Wow, so loud. Okay. Welcome back before the break. Glad that you are still here. Just a reminder, we will coming after the recess. I hope you have a good recess. Maybe relax a bit or catch up some of your work. And after the recess week on our October the 3rd, the Thursday morning at 9 a.m., we will have a quiz. Okay. The quiz is paper and pencil. So on that day, we'll come here and then we have some we will do one quiz. The quiz itself is half an hour. And what it's just one double-sided paper. And what will happen is there will be a chance that we may have too many students in this room. So some of you, maybe 10 or 20 of you, need to go for another tutorial room for the quiz. Okay. We'll send you the arrangement, but I think it's too early to do that. We don't need to do it now. So please be reminded when it's your quiz venue. We will actually announce probably after the break. And the quiz, everything, the scoop is everything before recess week, which including today and tomorrow. But usually quiz one will be easier. Okay, will usually more primitive. So don't worry too much about quiz one. And one very important thing is paper and pencil. I think nowadays we're not so used to paper and pencil quiz. Please bring pencils and erasers. That is somehow become a very difficult task for some of our students now. How to get a pencils and erasers, because we usually don't use pencil and erasers anymore. But please bring that. We won't provide you a spare paper for you to erase or change. And also, there will be some multiple choice, which you need to fill in the little circle with your paper, and you cannot change it if you don't use pencil. Okay, so please, very importantly, bring pencils, and preferably, please bring the 2B pencils. We are going to scan all your papers into soft mark, and then we'll mark there, use the machine to mark your MCQs. And then also there's a good platform to release all the paper back to you. Okay. So remember, okay, bring pencils. If you're kind enough, bring one or two more pencils. Maybe you will lend it to your classmate. It's closed book, but you can bring one A4 size cheat sheet. Okay. The reason for that is actually we don't mind open book, but if in our past experiences, if we can allow open book, people will print out all the 400 pages stack of note, just Gatsuma, print out everything, every lecture, every tutorial, even the cosmology pages, print out everything and bring it to the hall. Of course, first, it's very harmful to the earth. Second, we don't want to cultivate a culture that you only start learning in the quiz. Okay, so please do not do that. And also, that was the purpose for the cheat sheet, because actually our course, especially our course, you know that it's not based on memory. You don't need to remember a lot of things. It's mostly understanding. Actually, if you remember my first goal in my first lecture, I say I want to minimize your reviewing time. So if you come for lecture, you should be able to understand things, and you shouldn't need to memorize a lot of things and study. Okay, so that's our goal. I hope that you may find our lecture very long, 長氣, and explain things in details. But we hope that you understand after the lecture, you remember most of the things. Okay, you don't need to go and keep memorizing, reciting things to put it in your brain. So that's our goal. So very, very importantly, please bring a two B pencils. Is physical calculators allowed? I think it's allowed, but I don't think it's much use. We don't have many arithmetic calculation. Okay, feel free to bring, but I don't think we need any numeric computation. Okay. Again, the scoop is everything before the recess week. Okay, and this is probably unique for the cook. I give you a bit time if you want to scan the QR code for question, because we haven't been using it for so long. I think our lecture seems like to be too deep, and today we are also quite deep, okay? But I will try to reduce the volume of data today. So my goal is, let's see how far we go. I would prefer today we just talk about the augmented trees. Okay. Okay, let's start. Sometimes I also understand the material can be very difficult, and you have to concentrate for 1.5 hours. It's very tiring. Okay, so today we try to go slowly. Where are we? We are talking about a dictionary abstract data type, which means I want to arrange my data according to some keys. And these keys is going for you to search things, for you to modify things. And the main goal for that is you can access the data very fast. We said that we can access the data in a log-n time. And some more, we use binary search tree. There's a big reason to use it, and there's a big reason not to use it. Okay, so why? For binary search tree, we do have all the abstract data type operation, like queries, modify, insertion, deletion. However, there was one thing that is quite unique to binary search tree, and that's what keeps it still alive. What do I mean? If you go for anyone trying to search for the SDT or packages for binary search tree, do you know that there's none? For example, if you search for the C++ SDL, there's no binary tree. At least obviously there's no binary tree for you to use. Why? There's no. Actually, there is. You just don't know, because the set in STL is actually binary tree. Okay, but somehow they don't provide a real tree for you to use. And why is that? I guess one of the biggest reason is, first of all, if you go back to the ADT of binary search tree, you know that you can do insertion, search, modification, deletion. Actually, all this can be done by other data structure. However, there's one very unique and special features that keep binary search tree alive is successor and predecessors. Other data structure cannot do it. Only they can do it, but it's not O and not N, right? So only binary search tree can do successors and predecessors in log-n time. That means if you want to find the next or whatever, then you want to use binary search tree, and it will be achieved log-n time in balance or AVL tree. So we are all the way talking about, because like a linked names, like the binary search tree, they are called dynamic data structure. First of all, you can build the data structure, which means you have a set of data, you build the whole data structure. And dynamic, it means on the fly, your data structure will change. Do you notice that is a very important property? If the data set doesn't change, I can just sort it. I run one time of sorting, that's it. I don't need to organize them anymore. I just have to sort them according to the key. I can do most of 99 of my operations. But what if it's like the populations of real people, the people coming in, people getting out, then you need the data structure to be dynamic. And of course, you can search, select. We'll talk about select today. Select is not search. Some of you talk about the case select in the tutorial, right? Yeah. But there are big elephant in the room questions. We already have STL, not STT, STL. We already have packages. Why do we need to implement it? Why this evil professor in 2040 whatsoever, for 2040S, 2040C, 2040 asked you to implement it? Why? Well, you can give the very high philosophical answer. Oh, it's like primary school. You need to learn how to do 1 + 1 = 2 because we still have calculators. Yeah, you need to understand that. But actually, there was one more very important reason is, of course, the other very important reason is for interviews, job interviews. If you go to Google interview, whatever, they all ask you about this. Okay. Yeah. But the most important reason is, of course, how to learn really things like a computer scientist, the logic behind it. I think this is actually one real thing. It's not just for to convince you that you are not learning something rubbish. How to think like a computer scientist, I think today is an important issue because a lot of people can be web programmer, can be app programmer, can be back end, front end, whatsoever. They are not thinking like a computer scientist. And it turns out that what they implement for user to use is super slow, clumsy, or not scalable. And I think the most important items is not all STL are ready-made for your use. Today, we will talk about the whole lecture about some features that you cannot find in STL. Okay, so we can modify some existing data type so that we can add more functionality that we need. And why the STL doesn't have that? Because somehow, sometimes this augmented data type or algorithms are not like universal. That's why they don't have it. We call about this as the augmented data structure. Yeah. So a lot of programs require you to store additional data, additional structure to make the data structure works nicely. Of course, if you talk about data structure, it's hard to invent a new one from scratch. You usually just augment it. Today we talk about order statistics and orthogonal range search. What is augment? You know, my son's playing Pokemon mode, Pokemon Go, and then you know that we have a lot of augmented reality nowadays. And I think it was the dream of people using Google Glass that you can wear a glass and tell you the environment or even give you GPS or give you hungry go where. You just have a glass and they show you, hey, this restaurant have a 4-star rating or whatsoever. That's called augmented reality, which means you already existing have the reality, but you augment it. So the basic methodology of how to do augmented data structure, of course, you need to decide what is the backbone, what is the original or already real-made data structure you want to use. And you need to determine what is the additional information you want to add in. And then you modify this according to your new information, like insertion, deletion. You need to manage the new augmented data. And there could be new operations. For example, we have already operation like insertion, deletion, successor, but you may need some new ones. Let's try to use our data structure for a new operation called data sort order statistic. What does that mean? Order statistic means if I give you a set of items or integers like that, can you tell me the kth item? Kth means maybe from smallest to the largest. What is the kth smallest item? For example, what is the 4th smallest item here? Well, usually if you are using human algorithm, you will say, oh, the smallest item is 7. The next smallest item is 9. The next smallest item is what? It's hard to see, right? But it's 13. That's why the 4th smallest item will be 18. I hope I didn't get it wrong. Okay, I may get it wrong. Okay. Yeah, but that is what you mean by select K. Select the rank, which means rank K. I want the K smallest item. For example, select 4, then you should point to 18. Okay? So how to implement it? Of course, if you just do a sorting, it's very simple, right? I just sort it, and then I get the 4th item is the 4th smallest item. But of course, the problem is what? What if your data set can change? you can do quick select in our tutorial mentioned, we can do ON. We can just sort it, okay? Sort it, and the good thing about sorting is afterwards, every queries of select K is O1 because you sort it already. You want the 10 position, you go to the index 10. You want the 100 position, you go to the index 100 because it's already sorted, right? However, okay, let's talk about however. For solution 2, if you don't do any preprocessing, I just have a random arranged array. Of course, quick select will be ON. You don't need to sort it, but quick select in your tutorial we talk about can find the 8th rank item in ON9. However, it's too slow, right? If your N is very big. You can use these two methods, but the problem is the trade-off. Let's say how many pre-processing time. Because for the first one, whenever you have new data, you have to pre-process it again. So the question is, what if it's dynamic? That means I don't only want to get the case item. My data is dynamic. I can add things in. I can remove things out. Okay, if, for example, this data is all the salaries of Singaporean or Asia, then the population change, the newborn, the new people coming to job industry, the people who retired, you have to change. How do we manage the change in this? If you use solution 1, insertion can be ON. Why? It's not ON. I can use my section search to go to the right position to insert, right? After you insert, you have to shift places. Everybody have to yield and move one around to empty out a space for the newcomer. So you have to be, the worst case is you have to shift n items. That is insertion is ON. Of course, solution 2 is easier because random. I can just anyhow put the new item anywhere. And the similar thing goes for deletion. So our idea is let's use our what we learned last week, the binary search tree. How do we do that? So this one. Of course, the most naive way is you can do in order traversal. For example, if I select 3, what do? I just do an in order traversal lah. I go from I find the minimum and I just in order traversal. However, this would be still ON, right? Yeah, the simple solution is I search a minimum, which means I go all the way to the 11, and then I do in order traversal. If I want to select 3, I do 3 steps of in order traversal. However, what if I want to find the last item or find the median? If I want to find the median, how? Median is n over 2. No matter what, how you do it, I want to find the median, that will be ON. So you do an in order traversal, then you find 27. And the time complexity is O log n to find the minimum plus OK. Okay, K is the rank now. But it's very unfair, right? You want to find something in the first in the queue is very fast. You want to find something in the middle of the queue, then become very slow. And the worst case is we are being pessimistic with ON. That's bad. If you want a medium, it's n over 2, it must be ON. So that's come is to our augmented data. So what do? We add information. What information? The most natural one you want to add is maybe we just put the rank now. Okay, what does that mean? Here, I put the rank of everybody. Right? It's most easy. So now what do I search? If I want to search free, what do? You can search based on the rank, right? You're from the root. The root is rank what? The root is rank 5, right? And you want to search for rank 3, where should you go? You go left or right? You are at the root, which the roots tell you the node 41 is rank 5. And you want to search for rank 3. What do? You go left, right? Because all the left is smaller than you. That means all the left is rank 1 to 4. And all the right will be rank 6 and above. And you are searching rank 3. So I'll go left. Okay? I'll go left. If current rank is larger than 3, I go left. Otherwise, I go right, right? So for example, like this, if this rank is 5, so I go left. So I go here. Now I'm at 20. 20 is rank 2 in the ranking. And now I want to search for rank 3. Remember that? So I go left or right? Because I'm at rank 2, all my things on my left will be less than rank 2. I'm not searching for rank 2. I'm searching for rank 3. That's why I go to the right, right? And then now I go to 29. Oh, 29 has a rank 4. I want to search for rank 3. So I go left. At the end, I know what is the rank 3, and I search 27. Okay, so you can, depending on the rank of each node, you just search according. It's actually like you want to put the rank in each node as the key, and then your searching algorithm is based on the rank. It seems like working, right? But what's wrong? What was the requirement you were talking about? What was the problem? Remember, we want the data set to be what? Dynamic. Okay? Because we fixed so much rank in there, what if I want to do insert 5? What happened? Insert 5 at 5. 5 will be here, right? And then some more, you do some balancing rotation. Let's don't talk about it yet. What is the problem now? The rank of this is wrong because it's not 1 anymore. The rank of this wrong, the rank of this wrong. Actually, all the ranks are wrong. Why? Because you insert 5, 5 becomes the minimum of the whole things. And anything after that will be wrong. Okay, let's don't get that extreme. Let's insert something in the middle of the tree. But any items that have which is larger than the item you insert, all goes wrong. Because they will, any items that after the current inserting item will have to increase by 1. So what should we do? Should we go and update them? What would be the time complexity if we update all of this node? Then again, it will be ON. Yeah. Let's update all the rank of the node. That will be ON, right? So what do we do? So the same go for deletion. If you want to delete the minimum, then every rank will have to decrease by 1. So what should we store instead? Instead of the rank? One trick is, instead of storing the rank of each node, I store the size of the subtree. Okay, this is the trick. How can that solve our problem? First of all, what is the size of subtree? Actually, it's a very easy to be understood concept. Size of subtree is, you call it the weight of the node. The weight of the node means how many nodes are there in that subtree. For example, all these are leaves, right? The node 11, 27, and 50, they are all leaves. So they only have 1 node. The weight or the size of this subtree is 1. Very simple. How about this one? Oops. This one here. This one. This one is weight is 2, right? Because the subtree of 65. Let's circle out that out. You only have 65 and 51. So the weight of 65 is 2. So the weight of 29 is 2. You tell me what is the weight of 20? What's the weight of 20? 4, right? Thank you. But how do you find that? Do you go and count? How do you find the weight of 20 is 4? Yeah, I count out, right? That's 1, 2, 3, 4, right? But what if 11 have a very big subtree, and then 29 also have a very big subtree? Is there a simpler way to find what is the weight of 20? Yes? The weight of what? Yeah, you have the weight of your left child and right child already. Your left child already tell, oh, this is my society, my family. I already have so many members. The right subtree also, the right child also tell you. Because 11 already tell you the subtree has total number of 1 node. And then the node 29 already told you there is my whole subtree is 2 nodes. I just need to care about these 2. And what is the weight of 20 then? Is the number of nodes on my left subtree plus the number of nodes in my right subtree plus 1, including myself. So I don't have to go traverse the tree to know that how many nodes I have. I only need to know my 2 immediate children, so I will know about that. So now you tell me what is the weight of 41? Instead of counting the whole tree, I know the left of 41 has 4 nodes because the node 20 tell me is 4 nodes. The node 65 tell me is 2 nodes. So my root 41 will have 4 plus 2 plus 1 node. Okay, so it's 7. So I don't have to traverse the whole thing. So that was my strategy. But go back to our problem. How will it solve our problem? Okay, so first of all, the weight is, if you have no children, your weight will be 1. If you have some children, your weight will be your left child's weight plus your right child's weight plus yourself plus 1. Okay, so that is the calculation. Okay, go back to our problem. Now, I have, for example, from the start, because at the start you only know the root, right? From the start, you know you have 7 nodes in your whole subtree, and now I want to say select 3. What should I do? You can do nothing. That doesn't give you any information. I have 7 nodes in my subtree, then what? What? I know nothing. It's not helping. Okay? Why then? Why I'm bringing you to that? Because when you search for the rank, you do not depend on your own weight. Think about this. You have no idea what is that in this unless you ask your children to help. Does it give you more information? What information does it give now? Your left child has 4 nodes. What does it tell you? What does it tell you about the rank of yourself? 41. Let me rephrase it or restate it. You know your left child has 4 nodes. What is your rank? 5. Why? You have 4 items more than me. Then I'm rank 5. Is it okay? So what you can do is, instead of depending on your own size, you ask your left child, hey, how many siblings are smaller than you are? Ask him. You say 4. If you are 4, that means that 4 nodes smaller than me, then I'm rank 5. Okay? So you use this to calculate your own rank, which is like the previous trial that you record your rank. But I don't have to record my rank. I will use this to calculate my rank instead. So from here, I actually know that actually the right child doesn't matter. The right child will tell you how far away from the end, but because we're talking about the rank, it's counting from the beginning of the queue, so it doesn't matter. You only your left child. How do you know your own rank by your left child? It's very simple. Rank in yourself is your number of nodes on your left child plus 1. If your left child has 4 nodes, the third node must be in the left subtree, right? Because if the left child has 4 nodes, you rank 5. If you rank 5, if you want to search for rank 3, you go left. Just like the previous example. Okay, now let's proceed. Let's see, is that simple? Now I go left. Now we are at the node of 20. Do we simply do the recursion? Well, in node 20, you can do the recursion like this because your left child is 1, right? So that means 20 is rank 2. Okay? It looks trivial, but I hid a trap for you. Now we want to select the third item in the tree. And now I know that 20 is rank 2. So that means all the left item of 20 will not be what I want. And that's why I go right. 20 must be rank 2. I go right. The third item will be in 20. Okay, now I'm stuck. Why I'm stuck? Why I'm so stuck? Can I do select 3 at 29? Select 3 means what? I want to find the third item at 29. Wait a minute, 29 have only 2 items. What went wrong? Something went wrong. Yes, something went wrong. It's not a question. Something went wrong. What went wrong? Well, because go back to 1 items here, you are at the 20. You say, I want to select the third item. But when you go from 20 to 29, you reduce your data set. You reduce the data set to the subtree, which is only the subtree of 29 and 11. But in the process of doing that, you eliminate 11 and 20 in your whole data set. That means I eliminate 2 of them. And I cannot search for 30 in the subtree of 29 now because I removed 2 of the smallest item. So I cannot do this in here because I want to select the third item in the subtree of 20. And when I go to the right of 29, I actually skip 2 items, which is the 11 and 20. That's why here, this is an important step. You go to the child, you have to find a smaller rank. You skip 2 items. That's why instead of finding rank 3, I need to find rank 1 because I skip out 2 items. Okay? So that is the, for example, let's say, not a very appropriate example. Imagine that I have a primary school and I have a secondary school. I clearly arrange all students, okay, in the academic performance. I want to find the 1,000 student who is the best or who is the worst, okay? Worst lah, let's say worst. Because the primary students should be worst, right? So after I search for the whole data set with the primary school and secondary school, I figure out that the 100,000 worst student will be in the primary school because will be in the secondary school because the primary school only have 100 students. So I focus in the secondary school. But can I still go on search for the 1,000 worst student in the secondary school? I cannot, because I eliminate 100 students from primary school already. So I need to search for the 900 student, which is the 900 worst student in the secondary school. I know it's not a very good analogy, but because you eliminate 11 and 20, you cannot select rank 3 anymore. Now you are selecting rank 1 in this subtree of 29. And if we, so this is only the very big step you have to consider, and it will become like that. You can actually think of the problem now, I only have this subtree. Because actually every recursion you can think of, you only focus on that subtree. And now I select 1 and that. So rank 1 in this subtree, how? Use the normal calculation. From your left child, you know that 29 is rank 2, that's why you go to left. And reach 27, and ta-da, you find that, okay? But wait a minute, why don't we need to do that in the first step? Remember the first step? When I go from 40 to 20, why didn't I need to do that? Because when you go from 41 to 20, you didn't eliminate any candidate that is smaller than you. So you don't have to do that. So you only have to do this step. This step, this step, this blinking one. You only have to do this step when you are traversing down the tree when you go right. When you go left, you just don't have to change the rank. Okay. So select this first. Your own rank is equal to your left child plus 1. So if very lucky, you are the rank you are searching for, bingo, right? So you can return the item you're storing in your note. Otherwise, of course, if the K rank you are searching is more than your rank, you go left. Okay? Otherwise, you go right. But when you go right, you need to search for the rank K minus rank. Rank is your own rank, okay? K minus rank, because you are eliminating, because your own self is rank, so you eliminate rank items, so you have to search for the K minus rank item in your right subtree. Okay, so that is the whole algorithm. So for example, how do I select 9 now? Another example. And you know that what is the rank of 41? The rank of 41 is 5, right? Because from your left child, you know rank of 41 is 5. So rank 9 will be on my right. So I go right. I go to the note 65. However, if I go to select 9 on 65, they will be wrong. I need to do this. My own rank is 5. K is 9. So when I reach 65, I need to select 9 minus 5, which is select 4 on 65. So I select 4 on 65. And now, because I know 65 is rank 2 in the subtree. Can you see that? How do I know? 65 has a left child of rank 1. Subtree. 65 has a subtree on the left with a size 1. So the rank of 65 is 2 is own subtree, not overall, not globally, okay? 65 has a rank 2 in its own subtree. That's why I go right. But I'm selecting 4. If I go right, I need to minus again. So when I reach the note 75, I need to select 2 instead. Okay, so I recursively do a select 2 and 75. And now I stop already. Why? Because 75 have a left child of size 1. That means 75 is rank 2 is its own subtree. Then I stop at 75. And 75 is the overall rank 9 in the whole subtree globally. Okay? And okay, so that's select. Select is I give you the rank K. and please find me the item. And I have a reverse function. I give you a key, find that node, but can you tell me what is the rank? How do we do that? The reverse function, right? The first one is I tell you find the 100th item for me. But the second one is I give you an item. What is the rank? How do I find the reverse one? For example, how do I know what is the rank of 27 here? Like, how do we do that? Yeah, I can go counting, but of course, we don't encourage forced counting. What is the rank of 72? First of all, we can find mean, then do in order traversal to 72, right? Of course, then the complexity will be ON. Because what if the item I want is in the middle, in the median, or the end? So it's a bad method. Idea is I find all the numbers that is more than that. Wait a minute, aren't you doing the same thing just in order traversal? Do we need to do that? Notice what I say in different. Do I need to find all the nodes that are smaller than 27? Or do I only need to know the number of nodes that is smaller than 27? Does it ring a bell? I don't need to enumerate or traverse all the nodes. I just need to know how many nodes. Those are two different things. How can I do that? Let's say I want to find this rank. First, the node V may have a left child. For example, I want to find the rank of V, right? The rank of V can have a left child, and its own subtree, V will have the rank of its left child size plus 1. This is what we established, right? However, this is the local rank in the subtree of V. V, you can see here that has other item that is smaller than it. Then what should we do? This is what is smaller than V. What are the other nodes smaller than V? What are the other nodes that is smaller than V you care? Well, this one, is it smaller than V? No, 29 is larger than V. This node, is it smaller than V? This node, is it smaller than V? What is the property of the node that is smaller than V and not smaller than V? The node 41 and 29 are bigger than V, right? They go left. They go left to find you. What about node 20? They go right to find you. You see that? The path going down, some go left, some go right. The one that go right is bigger than V. The one that go left is smaller than V. So you concentrate on the path. If you go up the parents, if your parent S is your parent of his left child, that means he's bigger than you. Otherwise, you can ignore them because they're bigger than you. What I want to find is how many nodes are smaller than me. So if any nodes that go right to find me, for example, this S node, I want to know how many nodes are there. And it's very easy. How many nodes in S is more than V? You just need to know S left child, right? S left child will tell you how many nodes. So when we go over the parent, that the current node is the right child, S, the left subtree of S will be smaller than V here. And all I need to know is the weight of its left node. Do I need to go into the left subtree and search for all the nodes? I don't. I just need to know how many. So I add them up and go up. So the rank function will be, I have this rank, that is the node left plus weight. This is my own rank. While the node is not null, I do this. If the node is left child, I do nothing. If the node is right child, I add the rank of the parents left. And then I will continue to go up to the parents. Okay, so it's like inversely traverse back to your parents to get the rank. For example, what is the rank of 75? First of all, how many nodes are smaller than 75? It must be included is left child. So its left child is here. Sorry. His own rank is 2. And then when you go up, because his own rank is 2, because he have a 1 left child. And when you go to 65 and his all left subtree will be smaller than you. So that's why here I will add the rank of 65 here to that. So that's why my rank now is 4. Do you see that 75 is rank 4 in the subtree of 65? And now I move up 41. 75 is rank 4 in 65. How many more nodes are less than 75 if I include all the nodes from the root? Then I ask 41, hey, 41, what is your rank? 41 has a rank 5. And that's why all these nodes, I don't have to traverse them. I just need to visit the left child, which is the node 20. I know that is rank 5. And that's why finally I rank 4 because it's the number of nodes on the left of 3. 1 is 41, and that's why finally I know the rank of 75 is 9 in the whole globally. Okay, so that's how we calculate. This one you may need a bit more exercise to get familiar with, but the algorithm itself is very simple. Okay, go back to our question. Why do we need to modify it? You can see that we can create new operations like these queries, and we can modify the data structure to maintain the data we want. Now the new additional functionality is the rank, and we can actually use that in this new augmented one. Okay, and we have to maintain it. How do we maintain it? What do we mean by maintain it? Because now we have well set, right? What if I add a new node? Is it okay? I just leave it there. What are the nodes that is affected? The augmented data of the weight is being changed. Which node is not correct anymore? Which weight is not correct anymore? You can see that all the parents. For example, 41 is not weight 7 anymore. 50 is not weight 1 anymore. But then it's easy because what I need to do is after I insert 52, I just have to update all the parents going up. Yeah, I have to update all the parents, but the good thing is if you have a balanced search tree, how many parents do you have? Log n, right? So I just need log n to update all my parents. Now the weights are correct. But what's wrong? Wind back to your previous week, last week. What's wrong? Yes? Yes? What's wrong? Yeah, what's wrong? Imbalance. Now the tree is imbalanced. So I do rotation. How do I do rotation? So I do rotation, right? For example, right rotation. Can I maintain the weight during rotation? How many nodes do we have to update for the rotation? Do we need to update all the nodes in the subtree? For example, you can see that if all the subtree of this green purple and red are W1, W2, and W3, right? Then the orange node will have a weight of W1 plus W2 plus 1. And the red node will be W1, 2, 3 plus 2. After right rotation, the green one need to modify to this new weight, and the red one just need this new weight. And that means after one rotation, you just need to update 2 nodes. And that's it. Okay, so you don't even need to update the parents or the ancestor. So maintaining this with our rotation whatsoever is easy. That's why this size augmentation is good for AVL3. And you can maintain it on the fly of all this data. Okay, so we are going to talk about the next things, which is even more mind-blowing because we are going up one dimension. But I think it's a good time for a small break, and probably you may have some question or whatever, but we'll add in some of the exercise in the tutorial, okay? So let's have a small break and we go for high dimension. Yes, let's continue on a higher dimension. Sorry to say that this is actually my specialty. My research is going up dimensions, okay? My PhD thesis is how do you find an object in 4th dimension or n dimensions, and how do you do a molecules there, okay? So that was my thesis. Let's talk about range search. Don't worry, I think this will be easy if you can understand the previous one, okay? What's range search? Very simple. Let's state the problem. Range search is you can arrange the keys, right? I want a section of it. For example, if your item is arranged in the key, I give you A and B. Please give me all the data within the range of A and B. For example, for all the students here, after your next week quiz, I want to find all the students which have the quiz mark from 40 marks to 70 marks. I want all the students' name between that range. This is called range search list query. I want the student's name. This is easy. Why? Because it's log n plus k. What does that mean? What's log n plus k? First of all, how do you do it? Very simple. You can actually search for A first. Go search for A and then do an in order traversal until B. Does it make sense? Okay. I want the range A from B. So for example, if I want to search all the Singaporean having the salary from 2,000 to 3,000, what do? I search for the Singaporean with salary 2,000. Then I do an in order traversal according to his salary, 2001, 2002, 2003, until the Singaporean has salary 3,000, then I stop. But the time complexity will be first. I need to search for the first Singaporean that have salary of 2,000. Then why is it K? Because actually you don't know how many people are in the range. The number of the people in the range determine how long your output is. So this types of algorithm is called output-sensitive algorithm, because your algorithm's time complexity actually depending on your output. If you have only 2 Singaporeans within the range, you're very fast. But if all of the Singaporeans are within the range, sorry, your algorithm will be ON because it's all Singaporean or half of the Singaporean, okay? So this one is super easy. How about I just need to count? I just need to know number of people. How do I do it? Actually, it's an IQ test. Can you do one very simple solution according to our previous 1 hour of lecture? One very simple solution. If I want to find the number of people with salary from 1,000 to 3,000, how do I do that? I just need the number. Yes? Hey, you should know it. Yes? The rank of what? Yes, you find the rank of A and rank the rank of B and minus. Is it okay? The one, for example, let's say here, after the quiz, I want to find the number of students from 40 to 60. First, I find the rank of 40. For example, I use ascending order, so the one who get 40 marks is rank 10, right? That means it's 10 students less than 40 marks. How many people getting 60 marks and below is the rank 60, right? Let's say there's 100 students getting 60 marks and below. But then this 160 mark, this 100 student getting 60 marks below, including marks that's less than 40. So I minus the number 40. Okay, so that means 100 minus 10 is 90. We got 90 people between the mark, between 40 and 60. So it's very simple. I just need to find the rank between them, okay? So just rank B minus rank A plus 1 plus minus 1, that one you need to see whether A and B are actually in the tree. Okay? If A and B are not in the tree, you may need the successor or predecessor's function. Okay, let's see. We are doing what we call a one-dimensional range search. I want you to think about that. What it really does is your key is actually data points. But luckily, it's one dimension, so all the data points in a straight line like that. For example, if I want to find a range search, I actually find a section of this. I want all the data points within the range. Four-dimensional data search is your data point has an XY value. And I want to find a box, which is a two-dimensional rectangle. What are those points inside that queries? Then you have an X range and you have a Y range. So it's called multi-dimensional range queries. I don't know anyone do all those. Anyone using any of this dating searching? You usually need to do some searching. For example, not dating searching. Maybe you search for Hungry Go Where. What is the price range? Or you want to search for something. Sometimes you want to state a range. For example, if you want to find a match, I want my potential date has ages between 25 and 45, okay, and 30 whatsoever. So that if you put the points on the data, that the X values is the height and the Y value in the age, that means I want the data point within this range. In the same things, same time I want my height is between certain, then I actually create a rectangle. Okay, of course, it's not depending on height or whatever. It can be any range of your data. It can be your salary. It can be your educational level. It can be where you live in Singapore. Okay, so it's called multi-dimensional queries. If it's two-dimension, you can think it's a plane. But you can think it about the three-dimension is the 3D space with points, or even four-dimension, fifth dimension, and so on. They're all the same. How do I get this box fast enough? So first, we'll build a PSD according to the X. What does that mean? If I just depending on one dimension, actually, do you notice that when I have a node, let's say the root is 25, what it really does is it actually cut the space into half. All of the left, whatever later, all the subtree there are in the left subspace. All on the right node are on the right subspace. So here, when you cut some more, I create a node of 12. 12 actually create two other subspace and so on. Each of the nodes you create is representing a new, we call it half space. So we cut this according to X. But sadly, it's not enough for our 2D range search because we cannot only find a range of X. We need to find a range of Y. Now what? Here is where see whether your mind will explode. Okay. First, I keep a subtree. No, I keep a tree that is divided by X. For example, you see 40, right? 40 have a subtree of its own, right? 26 and so on, right? Okay. We have all these data points. Now, I will augment the node 40 by adding in a new data into that. Before that, I add the weight, right? One integer. Now, inside the node 40, I will add a tree into it. Can I? No one stop me. I put a tree in the node 40. And this tree is the tree of all the nodes in the subtree of 40, but they are arranged by Y value. Is it okay? So roll back a bit. This green one on the left is arranged by the X value. And then for each subtree, like 40, they will have a subtree. Inside the node of 40, I've put inside a tree, I diminish this tree inside node 40, which is a tree that arranged all the subtree node in 40 by Y. Okay. And how do I use this? Very simple then. If I want to find any queries, whatever, what I can do is first I do a range query in X. So it's like that. Okay, sorry. I do a range query in X. For example, I will do a range query in X so that I know that, oh, maybe this node are within the range of X. Then I go to all these nodes to find the points I want in the range of Y. So then I can eliminate a lot other nodes. And finally, I know it's a bit whatever it is hard to so at the end of the day, it's log n squared. Because you need log n to find the X node. And in each of the X node, you may need to go in again. But each time, at most, for each of the node in the log n, you need to find log n again. So that's why it's log n squared. Log square n, that means log n times log n. And then the time complexity is, if you want to output all the queries, it's log n to find all the range in X, and another in each of the X node, you spend another log n in the Y tree. And finally, you need to list out all of them by in-order traversal, right? So that's why the K. And of course, the small problem is now your space is n log n. Why? First of all, what was the space complexity for our ordinary binary tree in last week we talked about? ON, right? Because it's n node there. You store n node. But now in each of the node, you still need to store one more tree. So your time complexity, your space complexity actually has to be increased to n log n. The small problem is if your data is dynamic, the set reality is your modification can be even to ON. And actually, you can so-called extend this to n dimension. That means I don't only want 2 dimension. I can have tree of trees of trees of trees. That means after each time you embed one of the tree inside this one. For each of the node on the Y tree, you put in a Z tree. And one more dimension, you just add one more layer of tree in that. And finally, if you go for n dimension, this is the general queries. And this is not fantasy, okay? Not just imagination. You know that in all your search, I don't know whether you search for dating website or you search for cars, even you search for hungry go where, easily you have many dimensions you have to search. And you give out all the list for some hungry go where. You want to search one of the dimension is what type of food, Indian, Chinese, Japanese. The other dimension is what's the price range. The other dimension is maybe what is the distance to your home. Another dimension is what. You actually add in all this is actually an n-dimensional queries. And if your number of data is big, you have to do this queries, and the query build 3 times and space will actually be this log d log to power d n plus k. Okay. I hope it didn't burn your brain, but it's an interesting topic. And the good thing is to increase its dimensionality is, I don't know. Nowadays, people don't like that because we all computer scientists, mathematicians are all going for AI. Anything is AI. But on the other hand, I think nowadays people are being short on the dimensionality, the 3D graphics programmers, and real geometry programmers, industrial processing, and so on. If you're interested in this direction, please find me for an FYP, okay? So this is an XKCD guide about dimension. How do they do the times and so on? For example, they say a 2-dimensional object is a photos. And then a 2-dimensional object with time is actually TV movies and so on. So I think it's quite interesting. And XKCD is a very interesting comics for special geeks. Okay, let's see. I don't think questions. Oh, is it only MCQs on? No. You have MCQs and you have true and false, and you have 3 essay questions. That means I will ask you a question you to answer. And those are problem-solving questions, which means if you went to the tutorial, we have some question like pancake flipping. Did you do the birthday question already? Yeah, those questions. Yes, you will do that. I will list your question. Please give me the algorithms or what data structure you will use to solve that. This is one of the course objective, but usually for the beginning course, we won't go into too deep. Okay, so we'll have that. I think it's allowed, yeah, allowed. Stream allowed. You already have the announcement for that. Okay, you already have the announcement for that is allowed. Okay, so I think that's it for today. I know it's a bit